Okay, today we're going to look at um, the identity matrix kind of in a different way. It'll really help with some stuff in the future. It's going to become a very, very useful tool to start thinking of a matrix in this fashion. This is specific to a transformation matrix, um, specifically for graphics. And when you see it, it'll make a lot more sense. It's not going to make things easier right now per se, but what it's going to do is give you a different understanding of kind of how to look at it. So let's jump over to the board and I'll show you what I mean. So let me remove this problem for now. All right, so we're just looking at this square in model space. Okay, so he's defined with his origin here is at the center. We're going to say that he's of, I don't know, length 1, so this is 1/2 out, and this is 1/2 out in this direction. So we're going to start by just looking at the identity matrix. And what you want to do is, well, let me just label it and then kind of explain this. So let's let this first column vector here represent the x-axis. The second column vector, let that represent the y-axis, and let this last one represent the origin. And let's break that down a little bit. If you watch the other videos about kind of the homogeneous coordinate system, we said that a point was defined now in 3 dimensions, but not really. It's x and a y and a w component. But the w component was used to differentiate between a point and a vector. So it's 1, right, if it's a point. And if we had some vector v, then we'd have some x, which we're just going to call s, as to not confuse them, some y, which we call t, and some w, which is 0 for a vector. And if you recall, to recap the reason why, this vector and this point can both be multiplied by the same model to world matrix, which can go through a scale, a rotation, and a translation. But what's cool about it is if you multiply a vector by that matrix, it'll only be affected by the rotation and the scale portion of it. It does not get affected in any way of the translation, which makes sense because a vector can exist anywhere. It doesn't really have a real position. It really just represents a direction and a magnitude. As for the point, though, because that 1 is here, the point does actually get translated, scaled, and rotated out. So this is why this distinction exists. But now take this knowledge and kind of look at the identity matrix and realize that, yeah, this right here has 0 in its w component, and so does the y-axis. So the x-axis is a vector, and that makes perfect sense. I mean, the x-axis is right here. It's this vector. Okay. And it is this vector because look, it's 1 on the x, no y component, and it's a vector in homogeneous coordinates. So it defines this unit vector right here. And then the y-axis is the same. There's no x value. There is 1 on the y, and it is a vector according to those rules. So, this is what the identity is showing me right now. It's showing me an x-axis, a y-axis, and then we have an origin, and lo and behold, this is a point. It's got a 1 in the w component, and it's located at, well, 0, 0, which makes perfect sense. So here's our origin. So what we're really doing is saying that when you look at the identity matrix, you're showing an x and a y-axis that are set up in the way that we best understand in the Cartesian coordinate system, with an x to the right and a y up. And, an origin that just sits at the center, which we know because the objects in model space are defined with the center to be at this specific object's center. So this is the origin at the center of the object. So start thinking about it like this. When you see a transformation matrix, you're seeing that the things that are occurring to this vector, this is how the x-axis was affected by that transformation. This is how the y-axis was affected by the transformation, and this is how the origin was affected by the transformation. So later on, we're going to start looking at things like, it's going to be important to say, where does the x-axis go? Where does the y-axis go as a result of the transformation, and where does the origin go? So these are really going to help us build transformation matrices in the future in an easier manner. So that defines, how we're going to look at it. And I'll show you real quick with this problem that we did in the previous video. This pretty simple one. I'll do it the long way just to get an answer. Well, it's not any longer per se. Just I'll do it the original way. There is a scale, so 2, 1/2, and 1. I'll do this quickly, so bear with the handwriting if it's bad, which it always is. So rotate by 90 degrees, so cosine of 90 is 0. This is minus sine of 90, 1, 0. Okay, and we translate by 1 minus 2. Okay, multiply all these together, we get 0, 2, 0. Let me write this somewhere where I want to keep it. Let's put it up here. We get 0, 2, 0. We get minus 1/2, 0, 0, 1, minus 2, 1. Okay, so this is the model to world matrix. Okay, so now let's look at it in a different way. Let's look at it by saying that, all right, we know that everything, right, is scaled. A point or a vector can be scaled 2 on the x and 1/2 on the y. Well, this is like saying I'm taking this x-axis and making it twice as big, and doing that's going to take everything else out twice as big, and then 1/2 on the y, so we're just going to like downgrade the y-axis and just cut it in half, and then it'll end up here and other things will follow. So we're going to look at that now and say, okay, well, let's take them as original vectors, right? So x is 1, 0, 0. Well, if we scale the x-axis, right, by 2, then we end up with 2, 0, 0. Okay, scale the x-axis by 2, right? Scale the y-axis by 1/2, so our y, so where do I want to do it? Right here. Our y-axis as a vector, just becomes 0, 1/2, and 0. If you really want to look at it, I mean, think about it. If you can scale a point, we said that, but our point's at the origin when we perform the scale. So multiplying 0 by 2 and multiplying 1/2 by 0, also, I mean, you're not going to change the origin. So the origin's unaffected. So we leave it alone. And this is what happens to the x-axis, the y-axis, and then the origin is still itself. So we move on to the rotation. The same thing applies here. If you look at it, we've rotated this object about the origin in the world, which is 0, 0. And since we haven't moved the origin yet, you rotating something around itself is not going to affect the point that you're rotating around. So the origin's also unaffected by the rotation. So we're really just going to rotate our x and y vectors by 90 degrees. And we're going to do that, by multiplying the x and y vectors by the rotation matrix, right? So we get our like 0, minus 1, 0, 1, 0, 0, like so. We take, 2, 0, 0, and we multiply it by that, right? So we get, this is 2 times the first vector, so we get 0, 2, 0. And that's our new result. And then this is 1/2 times the second vector, so you get negative 1/2. That's a 2, 0, 0. Okay, so this is what our x-axis has done. This is what our y-axis has done. And then our origin is still 0, 0, 1, so we're going to leave it alone again. And then we look at the translation. And as I mentioned before, we've got 2 vectors here representing the axes, and they are not affected by a translation, so we don't even really need to think about how they're affected by it, because they're not. Only the origin is, and the origin is just gonna, when we were translating, we're taking this point and we're moving it, 1 to the right and 2 down, and that's exactly what we're gonna do. So the origin, which starts at 0, 0, and it's 1, after all this, just goes to 1, minus 2, and 1. And now that we know, look, what happened to the x, what happened to the y, and what happened to the origin, that is the transformation, right? So if I put these all into a matrix such that the x fills this spot, the y fills this spot, and the origin fills this spot, I should get the same exact answer. And let's find out, if I didn't mess anything up. You get your x-axis 0 to 0. My y-axis is minus 1/2, 0, 0. And my origin went to 1, minus 2, 1. And sure enough, right, this is our model to world. So there are two ways to look at it. We look at it as an object that we make 3 of the standard, right, transformation matrices out of it, out of this definition up here. We multiply them all together and we get this model to world. Or we can really think about exactly what it's doing. How is the x-axis affected? How is the y-axis affected? How is the origin affected? And you can see that we get the same answer, and this will come in handy extremely well later. So make sure you take the time to understand what this matrix really represents, and how we can get this answer without even going through all of the matrix multiplications. All right. Next time I think we'll do some inverse matrix calculations, but using matrix decomposition. So because we know it's a transformation matrix, we can decompose it into those 3 matrices that got it there, and then we can perform each one of their inverse operations. And basically we're just going to use that to undo things. If you want to rotate, then you can rotate the other direction to get back to where you were. You do that by using the inverse rotation matrix. So until next time, see you then.